Okay, this is the geotech portion of Engineering 839, and I am going to start out with a brief review of soil mechanics so that we are all on the same page. Some of you may remember this, and then you can skip through the videos or skip through portions of the videos. Those of you who don't remember this will be a review for you so that you can do the assignments. So in other words, these videos are going to help you do the assigned problems. Okay. So let's start with what soil consists of. We have solid particles, we have water, and we have air. And so when I say the word soil, I'm talking about everything. I'm talking about solids, water, and air. If I say the word soil particles, then I mean the solid particles. So I will use maybe solid particles, soil particles, but those refer to the actual particles themselves, whereas when I say soil, I mean everything: air, water, and solids. So that soil means everything: air, water, and solids. Soil particle is the solids, and the voids are anything that is not solids, which is water and air. And this is the typical way that a soil is represented in a schematic, whereby although the soil really looks something like this, we separate out the solids, water, and air, and as we said, the combination of the air and the water is the voids. Symbols: WS is weight of the solids, WW is weight of the water, V sub S is volume of the solids, V sub W is volume of the water, V sub A is volume of the air, V sub V together is the volume of the water plus volume of the air is the volume of the voids. W is the weight of everything. The air is assumed to have no weight, so W is simply the weight of the water plus weight of the solids. V is the volume of everything, which would be the volume of the solids plus the volume of the water plus the volume of the air, which is the volume of the solids plus the volume of the voids. So these are with no subscript. So when there's no subscript, we're talking about the weight of everything, or the volume of everything. The basic terms: E is void ratio, N is porosity, small w is water content, S is degree of saturation, G sub S is specific gravity of the solids. Now, one of the purposes of this lecture is to fill in some holes that I have in my soil mechanics and foundation engineering classes. You can't cover everything. And so there are little things that I sort of didn't really cover that, for instance, can be covered on the professional engineering exam. And I want to close those holes and cover those things so that if you get a question on any of these things, you know what they are and you can solve the problem. So, and then, okay, so I don't really cover much on porosity, but that may appear on the professional engineering exam. What is it? It's volume of the voids over the total volume. Most of the time we talk about void ratio, which is volume of the voids over volume of the solids, but geologists like to talk about porosity, which is volume of voids over the total volume, not volume of the solids. And this comes up occasionally in various equations. So this is new. Water content by definition is weight of the water over weight of the solids. Degree of saturation is volume of water over volume of the voids. And like I said, specific gravity of the solids. And what is that? That is the ratio of the density of a solid particle compared to the density of water. So in other words, a rock is, like I said before, a rock is more dense than water. Why do you know that? Because if you throw a rock in a swimming pool, it sinks to the bottom. Well, how much more dense than water is a rock? Generally, it's about 2.5 to 3 times more dense than water, which means that the specific gravity of that rock is 2.5 to 3. So that is the meaning of specific gravity of the solids, G sub s. It's how much more dense is a particle, a given particle. Now, sand is a small rock, so typically a sand grain has a density of 2.5 to 3 times that of water. So it has a GS of, for instance, 2.7. Density, unit weight. You'll hear the term, they are the same. If we have gamma, it's simply weight over volume. That's the total density. Gamma D is the dry density. It's the weight of the solids over the volume. Total volume, notice. It's the weight of the solids over the total volume. It's not the weight of the solids. It's not the weight of the solids over the volume of the solids. It's not that. The dry density is weight of the solids over the total volume. And all soils have a dry density, even if a soil is not dry. Even if the soil is wet, it has a dry density. We just define it as, separating out the weight of the solids and the total volume. Remember, the total volume includes the volume of the voids. So that tells us what would be the density of our soil if it were dry. Same thing with saturated, gamma saturated, which is the saturated density, which means what we do is we assume that the degree of saturation is 1, and all soils have a saturated density, so we assume all of the voids are completely filled with water, and we get a density for it. So even if a soil is not saturated meaning that there is no air, we have a saturated density. We envision the soil to be saturated. We come up with a density for it. Now, the density of the solid particles, gamma S, it's not the same. These are not the same. Not the same. Gamma S is the density of the solid particles, and it is GS times gamma W. So, like I said, the typical number for G sub S is, for instance, 2.7, because the density of a single particle, a rock or a small rock like sand, is going to be about 2.7 times that of water. So, and then gamma W is the density of water, and you should memorize this, 62.4 pounds per cubic foot, or 9.8 kilonewtons per cubic meter. There are some interrelationships that can be used to solve problems. S times E is equal to G sub S times W. Now here's one that I don't normally cover. N is equal to E over 1 plus E. Okay, so the porosity is equal to E over 1 plus E. So, porosity and void ratio are related. And like I say, geotechnical engineers normally use void ratio. Geologists like to use porosity. Here's another equation. E is equal to G sub S gamma W over gamma D minus 1. I'm not going to derive these or anything like that. They were derived in soil mechanics. And gamma D is equal to GS times gamma W over 1 plus E. And that's equal to gamma over 1 plus the water content. Remember, small w is water content. Big W is weight. So do not get those mixed up. Small w is water content. Big W is weight. So when I draw a small w, this is water content. This is water content. Okay, here's an exercise. I suggest that you pause the video and work this exercise. This is what it is. I have a soil with a weight of 30.75 pounds, a volume of 0.25 cubic feet. Now remember, this is total. W is the weight of everything. V is the volume of everything. The G sub S refers to just the solid particles. G sub S 2.66. Like I say, it's close to 2.7 in this particular case. The weight of the solids is 28.01 pounds. And then, this is what you need to memorize. What we want to find is what is the density gamma, small w, the water content, gamma D, the dry density, E is the void ratio, N is the porosity, and S is the degree of saturation. So pause the video here and do your best to solve this, and I will give you the solution. Okay, assume you've made an attempt to solve this problem. Again, this is the given information, and this is what we're trying to find. And what's the solution? Well, the weight of the water is going to be what? Well, I know the total weight, I know the weight of the solids, so the weight of the water is the difference. So it's simply the 30.75 minus the 28.01. That gives me the weight of the water. The density, which is gamma, is defined as the total weight over the total volume. And I've been given those two numbers, and I divide them out. I get 123 pounds per cubic foot. The water content is weight of the water over weight of the solids. We've already come up with the weight of the water. And we have the weight of the solids. I divide those two. I get 0.0978. And we generally put that into a percent, so 9.78%, even though it's not a true percent. The gamma D is, by definition, weight of the solids over the total volume. We know the total volume, we know the weight of the solids. So we divide those two, we get 112 pounds per cubic foot. And E is the volume of the voids over the volume of the solids, or we can use the little shortcut equation that I gave you on the previous page, which is that. So look for the shortcut equations, and it can save you some time, for instance, on the PE exam. So we know all of these terms, we plug them in, and we get 0.482 for the void ratio. And then I can use the porosity is E over 1 plus E, which I just gave you. Plug that in, I get 0.325. Now we know the degree of saturation is volume of the water over volume of the voids, but another shortcut equation is that S times E is equal to GS times small w, and I can simply solve this little equation for S, and I get S is equal to GS times W over E. Plug those in and we get 0.54. So just remember, if we know the weight of the water, then we know the volume of the water. Why do we know that? Because we know the density of the water. So the density of the water is weight of the water over the volume of the water. The density of water again, is 62.4 pounds per cubic feet. So we know this, or 9.8 kilonewtons per cubic meter. That is known. Those are known. So if I know the weight of the water, I know the volume of the water. If I know the volume of the water, I know the weight of the water. So you can always remember that. These are all just weight and volume problems. So it's all about just getting the weights and the volumes. That's all you need. And you can solve every problem. If you got the weights and volumes, you can solve every problem. But now for gamma S, we know that it's weight of the solids or the volume of the solids. But what is gamma S? Gamma S is not known unless we know GS. So if we know GS, then we can say that if we know the weight of the solids, then we know the volume of the solids if we know GS. So because it's all about getting gamma W we know always. Gamma S, to get gamma S, we have to know G sub S. So just remember, so if you're given one, you can get the other one. And when I say given one, if you're given the weight, you can get the volume. If you're given the volume, you know the weight. Okay, so that was a quick review of that. Now I want to get into soil classifications and get us caught up on that. Remember, there are 4 kinds of soil. We have gravel, which is G, sand, which is S, silt, which is M, clay, which is C. And these two are coarse grained soils because they can be, they can be seen with the naked eye. These are fine grained soils. I cannot see a particle of silt or clay with the naked eye. Consider flour in your kitchen. If you pick up flour, you cannot see a single grain of flour with your naked eye. That is what silt and clay are like. They are fine-grained soils. And the other part of it is that these fine-grained soils, they interact with water completely different from the coarse-grained soils, the sand and gravel. If I take and I add water to sand, well, it doesn't really change much. It doesn't really change. If I add water to gravel, it doesn't really change. If I add water to the flour in your kitchen, it makes a paste. Completely different. So, same thing with silt and clay. If I add water to silt and clay particles, I'm going to make a paste. It reacts completely differently to water. So, the big particles, sand and gravel, small particles, silt and clay, fine-grained soils, coarse-grained soils. Now, again, some don't get confused though. We will talk about fine sand. Fine sand means small sand particles. Coarse sand means big sand particles. Fine gravel means small gravel particles. Coarse gravel means big gravel particles. So we sort of mix the terminology, but when we say fine-grained soils, we're talking about silt and clay. When we talk about coarse-grained soils, we're talking about sand and gravel. And then let me just say something about the sizes. Sand goes from a fine salt to a pea-sized particle. Gravel goes from a pea-sized particle to an orange-sized particle. So coarse gravel is like an orange. Fine gravel is like a pea. Coarse sand is like a pea. Fine sand is like a very fine salt in your kitchen. Now, this is new, just to comment. What you've learned previously in our soil mechanics class is the Unified Soil Classification System, but there are other classification systems that can be on the exam. There's the AASHTO, which is sort of an offshoot of the USCS, and then there's the USDA Department of Agriculture. So those can also be on the exam. So I'm going to describe those as well as give you a quick review on the Unified Soil Classification System. And the goal of the USCS is to get the symbol G, S, M, or C. That gives you half the problem pretty much. And then you need to get the second part of that's half the problem. The second part is to get the descriptor of it. Okay, so just to review, the fine-grained soil tests are the Atterberg limit tests, which consist of the plastic limit test. Again, the plastic limit is a water content. If you remember, this is when you roll the soil into a worm. So you get the soil into a worm, and that worm is when that worm is 1/8 of an inch in diameter, and it just starts cracking at 1/8 of an inch in diameter, then you have the right water content. So, and so that by definition is the plastic limit. So what you do is, remember, you roll the soil into a worm in the lab and make sure it just starts to crack when it's 1/8 inch diameter. That is the right water content. You figure out the water content by definition. That's the plastic limit. Now, strangely, it's a water content, but we don't use the percent. Just the way it is. With the liquid limit test, I'm not going to go through the test, but it's the water content that gives us a stiff frosting. So in other words, you've all frosted a cake maybe, and you have to get, you got to get the water content just right to frost a cake properly. If it's too dry, if your frosting is too dry, then it destroys the cake when you try to put it on. If it's too wet, then it's all runny. So you have to get the water content just right when you're creating a frosting. And it's the same thing with the soil. You have to, each soil is different. Interestingly enough, each soil is different. So in other words, for this, we're talking about clays and silt, so that's because it's a fine-grained soil test. Remember, I said you make a paste. You add water to the soil, you make a paste. And the thing is that one type of clay, like a bay mud, is one type of clay. It may need a lot of water to make a paste, whereas a different, say, a Boston blue clay may need not much water to make a paste. So each soil is different. It's not like the flour or the powdered sugar in your kitchen. Generally, flour is flour. I add a certain amount of water to flour, it creates a paste. You get it in the recipe. But soils are different. In other words, the soil in Boston is different from the soil in San Francisco. So you add different amounts of water. So in other words, the plastic limit for the Boston blue clay is completely different from the plastic limit. In other words, how much water needed to be added. It's completely different for San Francisco Bay mud. Same thing with the liquid limit. The Boston blue clay will have a different liquid limit than San Francisco Bay mud. And this is how we learn about the different types of soils, how they react to water, and it ends up to be important in our foundation designs and construction that we do. Okay, the plasticity index, PI, is the difference between the two, liquid limit minus the plastic limit. And now here's a new term that I haven't used in my classes, the liquidity index. What is that? Well, it involves the liquid limit and the plastic limit, but the liquidity index, LI, also tells us what is the soil in situ. So WF is the water content in situ. So in other words, the liquidity index tells us something about what our soil is at our site. Now, so let's look at it. Let's look at this ratio. Suppose the water content at our site is equal to the plastic limit. That means, so in other words, the soil at our site is in a state where it cracks. It starts to crack when making a worm. So what would the numerical value be? Well, if this is the plastic limit, then this is 0. So if our liquidity index is 0 or less than 0, what do we see? We have our soil at our site is sort of brittle. It's cracking. It's in a cracking type state. If our if our water content in situ at our site is equal to the liquid limit, then what? Then this ratio becomes 1 because it's LL minus PL over LL minus PL. It's 1. So if our soil has a liquidity index of 1, our soil at our site is at the liquid limit, then it means it's a frosting, which is soft. It's a frosting for our cake. It's soft. So the liquidity, and if this liquidity index is between 0 and 1, then it's in between, and we call it stiff. So the liquidity index using this will tell us something about what is the state of our soil at our site. Because when we do the plastic limit test and when we do the liquid limit test, we just take the soil that we get from the site, we add water, we subtract water, we do all this stuff to it. So it has nothing. When we run these tests, it has nothing to do with what the soil is like at the site. The liquidity index tells us something about the soil at the site, and we can use this little guide to help us. Okay, for coarse grain soil tests, we have our stack of sieves with the largest holes at the top, the smallest holes at the bottom. 200 is the smallest. That means 200 holes per inch. It's very tiny. It looks like a cloth almost. We pour it in. This stuff goes down. We then get a certain amount of soil on each sieve. We get a distribution, and we can classify. It will help us classify the soil by figuring out the distributions on the sieve. So if we look at the sieve numbers here, this is an exercise you can do, and what I want you to do is to plot this soil. So I'm going to show you how to do this one. So we have sieve number 4, 10, 20. As the number goes up, the holes get smaller, right? Because this is 4 holes per inch. That means each hole is approximately a quarter of an inch. This is 200 holes per inch. It means each hole is about 1/200th of an inch. So as the number goes up, the holes get smaller. This is the result of a test. The mass on the sieve in grams is this, and I'm going to make the other comment. Now, in this problem, I guess I didn't indicate it. We're going to start with 1,000 grams of solids. It's dry. The soil is dry here. 1,000 grams of solids. Now we run it through the sieves, and if we add up this total here, we only get 996.9. Well, what happened? We lost 0.31%. We lost 3.1 grams. that, they sort of get stuck to the sieve and this sort of thing. So when we run this test, sometimes they ask on an exam, is this test valid? If we lose too many particles, it's not valid. We have to lose less than 2% is the rule. So in this particular case, so this is also new material I don't cover in class, the loss is 0.31%, and since this loss is only 0.31%, which is less than 2%, we can say that the test is okay, it passed, in terms of the amount of loss. Okay, so this is the math on the sieve. We need to get the percent retained. Well, how do we get that? We divide each term by 996.9, and so the percent retained, you can all do this, are these values. We need then to get the percent passing or percent finer, same thing. And how do we get that? Well, if you remember from the class, what you basically work, the easiest way is to work from the bottom up. And in other words, if there's 1.4% in the pan, that means 1.4% has passed the number 200 sieve. So I just simply move this up here, because that means that I work across here. All of these numbers work across like that. And this is a little bit, they work across like that, and that means that I have I can see that 1.4% has gone through the number 200. That means 1.4% is finer than the number 200, which is what we're looking for in this column. And then I have 11.8 on the number 200 sieve, and I have 1.4 in the pan. That means that 1.4 plus 11.8 is passing the number 140 sieve. So I just add the 1.4 plus the 11.8, and that gives me 13.2. And I just continue up this, so 13.2 plus 22.2 gives me 35.3. I keep working up. Then I have 35.3 plus 21.4 is 56.7, etc. When I get to the very top, I should have 100. And then what I want you to do is to plot this column to get the soil type. So you can plot this on a plot that looks like this. You have to use the top x-axis. Don't use the bottom x-axis. The top x-axis gives us the sieve numbers, in this particular case, number 4, number 6, number 10, number 16, etc. And over here, when the holes get really big, we can't do openings per inch, so we have to go with the hole size. So 3/8 inch, 1/2 inch, 1 inch, 2 inch. So this is, you use this x-axis, not this x-axis, to plot the points. This is the percent finer, percent passing by weight, and here these are all percentages. So pause the video, and in the notes you have this plot. So go ahead and plot those points by hand on this. Okay, I'm going to stop here.